The fundamental theorem of algebra gets a very interesting different sets of treatments in various linear algebra books, and of course also in abstract algebra books. But in this video, I'm only going to talk about the cases where it gets described in linear algebra books. Now, I'm going to leave this video for myself more like as a marker for when I come back to another round later on. And so this is not the video where I have read every single one of these proofs in detail. This will be something that I plan to do at a later time. So in the case of Friedberg-Insel-Spence, the proof of the fundamental theorem of algebra is really just a rewrite of the proof as found in Baby-Rudin. So that's really all the dimension that it gets from FIS. And I did follow this proof, or tried to, and so it's really called the algebraic completeness of the complex field. And the theorem is all about saying that a polynomial in the complex field you can find all the roots. Whereas if you did it in the real numbers, and you had like an x squared plus 1 term, well, x squared plus 1 has imaginary roots, so that's not going to fly. So you cannot get all the roots out of a real polynomial where you can out of a complex polynomial. Yeah, and I'm not going to go through the proof, but I'm just showing here what it looks like. It's just the same as in FIS. Then I'll bring up the case of the proof in an undergraduate abstract algebra book, such as Robman. And in this case, he really mentions it as Kroneker's theorem, where it says, the next theorem states that all the roots of a polynomial f of x with coefficients in an arbitrary field k can always be found in some larger field E. And then he's got a little note about how the Kroneker theorem is really a generalization of the fundamental theorem of algebra. But I'm not going to talk about anything more here about how it is in this book, because the very large abstract algebra book by Dummit and Foot has 2 proofs of the fundamental theorem of algebra. Now in this case, it's already gone through some Galois theory by the time it gets to it. I've got that marker for another reason. And so it's right here in Dummit and Foot where they go. There's 2 proofs of it, and then there's 2 facts regarding the complex field. Every polynomial with real coefficients of odd degree has a root in the reals. That's what I was saying before, like x squared plus 1, does not fit in R. Then quadratic polynomials with coefficients in C have roots in C. Equivalently, there are no quadratic extensions of C. I don't really know what that means because I haven't done abstract algebra. But anyways, maybe some of you do. And so Dummit and Foot go through this particular proof and then outline the second proof and say right here, it was first proved by Gauss. The first proof, this one right here, comes from Laplace, and then the second proof comes from Artan. So there's 2 different proofs, and these proofs are different than the one in Baby-Rudin. Again, I'm not going to go into details because I have not read these. I'd have to read a lot of abstract algebra to be able to understand them. Then in the case of 2 of my favorite linear algebra books, one thing that I've noticed in the case of Huffman and Kuntz and Axler is that they have specific polynomial chapters, which is not the case in the other books that I have at my disposal. Another thing that I've noticed with the way polynomials are treated in all these linear algebra books, it's that the treatment is very different. So making a comparison for specific polynomials, especially when you get into eigenvalues, will get interesting, I think, when I get around to doing it. So anyways, I'll briefly show, in the case of Axler's 4th edition, which came out recently, that he's got 2 proofs. He's got the first version, which is the one from Baby-Rudin. It uses this technique of having the root be within a circle, and then you make that circle ever smaller and it lands on 0. I believe that's how Baby-Rudin does it. And then he's got a second version, which is more of a factorization way of proving it. Now, one thing that I noticed, again, there is a very brief chapter in Axler only on polynomials. I find that useful. And then also for Axler, after he does those two proofs, he does mention some more things that are related to the fundamental theorem of algebra. Then in the case of Huffman and Kunz, it gets a very brief mention at the end of a polynomial chapter. Again, Huffman and Kunz does have a polynomial chapter, but just to give you an example of how different the treatment is from book to book, and why, if I had a lot of time, I would do like 10 linear algebra books. In the polynomials chapter by Huffman and Kunz, they actually put in a lot of algebra, a lot of abstract algebra, and they talk about the Lagrange interpolation, which actually is in FIS. And they also talk about polynomial ideals. So this is where I had a second mark in Dummit and Foot, and this is it. So really, it looks like, okay, and again, I haven't taken abstract algebra yet. I haven't read it. It looks like ideals are to rings what cosets are to groups. I mean, if I read this theorem about the left ideal, right ideal, and the subring, this looks to me like Laplace's theorem. Is that what it's called? For subgroups and cosets. So anyways, I just wanted to make a mention of that this is something that is particular to Huffman and Kunz.